option for this, what it's going to look like. How is the shape I draw here going to look different than that one? I'm going to pretend like you guys are focusing so hard on your drawing. Exactly right. The functions are going to be on top and bottom, right? It's going to have something funky up here, something funky over here, but it'll have definite sides, right? Definite bounds for the sides on it. Which means when I look at this, since I have y over here, I'll be running this from c to d, right? And my top function will be g2 of y, right? g1 of y, so that when I set this up here, I'll write it down here, first integral is still going to be u1 y z, u2 y z, f of x y z, dx. The next one here will be running from g1 y to g2 y. What variable is that with respect to, though? Z, right? So this will be dz. And then finally, running it from c to d with respect to y. So we got type 1, which is where we cut it for z. We got type 2, which is where we cut it for x. What's our only other option that's left?
I have a question about it.
Yeah.
On this, how do you know which one's U2 and U1?
Oh, really good question. So you think about this being the x-axis, right? When we talk about which one's the second, which one's the first function, the second function is the one that gives us the most distance away from our axes. So if you think about, we know y2 versus y1, or f2 versus f1, because it's on top, right? Which direction is positive for x here? Out, right? So these x values are getting bigger, which means I should have the function out further, because I'm integrating with respect to x, right? The top one for x, the further one out from x is in a positive direction. That's a really good question. What a question. So impressed. Okay, type 2, we cut it across x. Final option is type 3. When I draw this solid, ooh, marker's dying. When I draw my solid, I'll use red. What is it going to look like? What do you think? What axis is it going to run around? Y, right? So it'll come out, right? It'll come out somewhere like this. Go ahead and draw it out like this. Maybe back. Oh, run around my y-axis, right? Make it kind of a funky edge on the other side. This is my third type, and that is if I take a cross-section of this junk, then it comes like here, and then it has this little weird side kind of over there. If I take the cross-section for it and I set it down, I guess this is a life lesson that I should start playing the cats on my life first. If I set it down, what axis am I going to have? What plane am I in if I do the projection of this? The xz, right? Because if I flatten this down, it'll be flattened against x and z. Exactly right. So what I'm going to do is write xz here, draw this out. That one's definitely who that is. What do you notice about my drawing versus what I have in the graph here? in that, on that set. It's going the opposite direction, right? So what happens here is when I do this projection, when I draw it out, this nice curved side should have the positive x values, right? So when I come over here, my positive x values should have the nice curved side for it. So it almost looks like it's backwards. If I could take this and I could spin it, I could spin this x over here and you could see it better. Unfortunately, I can't draw three-dimensional, let alone spin my three-dimensional shape. So we're screwed. I'm going to go ahead and I'm going to leave that there, and we're going to talk about the two options we have. Before that, though, we should set it up, I guess. We need to go ahead and label these. U2, further out, right? U1. What are these functions of? XZ, exactly right. I want you to notice that when I write these, I pay attention to the order. In a function of three variables, we go x, y, z, right? So when I write these out, I'm making sure that I keep some of that order, x before z, and so on. It'll make it easier for us to visualize in the graphic. That is the projections of them. So this integral is going to go from u1, xv, to u2, xv, f, x, y, z, z, y. Perfect. And I'll look at all that, and then all I have to do is integrate over some region D, dA, right? The order I do that in can differ. There are going to be two options. Option 1, when I look at it, x and z, is I can have curvy sides on it. If I have funky weird curvy sides like this, label them, right? This over here will be H1. This will be, sorry, that's H2. That'll be H1. What will these be functions of? What will these be functions of? They'll be functions of Z, right? I want you to think about it this way. And actually, we'll just leave it like this. I don't want to confuse this any more than we have to. The reason I can tell that is because these boundaries here are in terms of what? What are the boundaries for? They're boundaries for Z, right? These are my boundaries for X. So this is X equals H2. X equals H1. These are my boundaries for X. These are for Z. Wait, equals, right? Which means this here will be E to F, right? When I write out this integral then, writing it up here, and I'm going to run it first of all, U1, X3, U2, X3, F of X, Y, Z, dy, right? For this one, my next one is going to run from H1Z to H2Z. What differential will I have there? With respect to x, I'll dx there. Perfect. And the final one I use then is from E to F, UZ. There's only one other option. And you're probably getting the feeling that I can kind of start cheating here. Maybe keep that same there, but change my axes, X and Z. I'll have G1 and G2, which variable will they be of? G1 of X, right? Because these are going to give me my Z values, my height. So they have to be functions of X. Which means on the bottom here, where am I running this from? A to B, because it's X values, right? Which gives me the entire integral. Go ahead and write it here. U1 xz, U2 xz, f of x, y, z, dy, g1 x, g2 x, dz, and from A to B, dx. How many total options do we have for triple integrals? Six, right? I want you to notice something about the way you're writing this. If you get confused with where your differentials should be, this is a function of x and z, right? Differential is dy. This is a function of z. Differential is dx. Bounds for z. Notice I'm working my way out, right? I start on the inside, and whichever one I'm integrating with respect to is a function of the other two. Which means if I can find a function of two of my variables, I know I want to integrate with respect to the one that's left out. After taking that one out, whatever my function is with respect to, I integrate the opposite one. Now, this is really overwhelming because we have so many options. I think the best thing we can possibly do is look at an example and try and figure out which way we're actually going to integrate it. That is, which of these 6 methods we're going to use. I'm going to erase this. We'll go ahead and look at one. A word of caution when you're doing your homework with this. Each one can be integrated multiple ways. Which means when you come to class 15 minutes early and you compare with your friend, and they look completely different, that doesn't necessarily mean anything's wrong. Sometimes you just feel something's easier than another person feels, or vice versa. So the example we're going to look at. Evaluate the triple integral over e square root x squared plus y squared dv, where e is bounded by y equals x squared plus z squared and y equals 4. The important thing to remember here is just like with double integrals, this stuff in the center does not matter at all to begin with. No one cares about that to begin with. We're not looking at the actual function, we're looking at the domain, or the solid we're integrating over. That being said, what does that square root of x squared plus y squared make you kind of think of? Circle, and what does circle make you think of? Polar coordinates, right? So as soon as we see that oh, you guys made those best faces. Okay, as soon as you see this x squared plus y squared, you should be thinking about polar coordinates because it's a circle, right? We're going to tuck that back in the back. I'll even write over here polar. But for now, we need to go ahead and figure out how we're going to integrate this stuff. When we begin to look at how we integrate, the first thing we do is we draw the solid. This is where your 3-dimensional graphing skills are going to come in handy. Okay, to graph this, what we're going to look at is where it's bounded. It's bounded by y equals x squared plus z squared. Notice I've got a function, right? What is that function in terms of? X and z, right? I'll keep that in mind as well. Now this is a very specific type of function. If I cover up and look at the trace, I get y equals x squared, parabola, right? Cover up this one, trace, y equals z squared, parabola. What is that general shape? Two parabolas. Here, it's a paraboloid, right? Paraboloid. Okay, I think that's how you spell it. A paraboloid, right? Which axis is this paraboloid sitting on? Y, right? Because it's y equals, which means what I'm going to end up with here is a paraboloid opening along the y-axis, like this. Now, am I going to just keep going infinitely far with this paraboloid? Does it just keep going? No, because I know something, right? Where am I cutting it off at for y? At y equals 4, right? So I'm going to do is I'm going to draw my paraboloid here, and I'm going to cut it. At 4.